Today's lesson is about area between two curves. There are two different approaches to find the area between the curves. The first is in terms of x, and what will happen is once you draw all your curves, you look at the region of area enclosed by all curves. If the region is conducive to drawing your stripes vertically, meaning pick the curve that is considered to be the top. If, as you progress from left to right, the curve that you have defined as the top function is always the one you start with as you draw vertical line segments progressing from left to right through the entire region, and will always connect to the curve you deem the bottom of the area of region. And if that is consistent as you move from left to right, then that would be the setup for working in terms of x and using top minus bottom to find the area of the region enclosed. And we would do function f, or whichever function is on the top, minus function g, in this case because g is defining my bottom. Just like area before, you need where you start collecting area and where you end. Those can be intersection points between curves, as in the case here, which is at A, and ending points can be intersection points, or they can be curves themselves, some type of a line. In this case, we have a line that's a boundary, so we're stopping at B. For the side-to-side case, when I would do side to side as opposed to up and down, would be scenarios when you have curves that go around and loop over themselves from a vertical perspective. So in that case, I would want to do right minus left. Now, the reason we say in terms of y is because I'm going to get x equals. I'm going to say, what is the x value here? I'm subtracting it from the x value here to find the distance of this segment right here. Because again, area is coming from infinite rectangles being summed, and these little strips here are representing my rectangles. So to find the length of each of these sideways rectangles, I would have to do the x value here minus the x value here. So the right x value minus the left x value to get the height of my curve. So I'm going to do f of y, which is defined on the right, minus g of y, because that's the left-hand function. And again, I'm saying a to b, and the a and the b can be intersection points. Like this one here would be the a, if I trace over, and then the b would be the intersection point here, because they both happen to have intersection points and not lines. We're going to start with an example that can be done by either method. So I have my curve 1/2 x cubed, which is this cubic function here, and the line y equals 2x. If I do it by the method up and down, which is in terms of x, I'm going to draw vertical stripes to represent the rectangles building up the area up and down. That integral would be, whoops, that's a ginormous integral, the area from 0, intersection point here, to 2 of, and I always use parentheses to represent the height of my function, because what's going on here is all of the height. I need the top curve, which in this case is the line, 2x, minus the bottom, which is the cubic, which is 1/2 x cubed. Again, for the thickness, we need dx to represent the thickness of each and every rectangle. That will get me the area. If I choose to go side to side, so I redrew it down here and I want to go side to side, that means I'm going to do it in terms of y, because I need to know what is this x equal to and what is this x equal to. So I'll start with, because I always do right minus left, I need this x, this is the cubic. Y equals 1/2 x cubed. I need to know what the x is. So then I would say 2y equals x cubed. x is equal to the cube root of 2y. That is my right hand x value as an expression. The left hand is over here, and that's y equaling 2x. Well, what does x equal? X equals y over 2. So now my integral to find the area goes from 0, because they're both intersecting at 0, x or y, but now, since I'm going side to side, everything's in terms of y, I need that y value up here. So I go to my graph, the y value at the top is 4, so I'm going to pick 4. The heights of each of these rectangles, they're going side to side now, so the height is the right, which is the cube root of 2y, minus the left, which is y over 2. And then I'm going to use dy to represent the thickness of each and every rectangle. Now the interesting thing is you can type it into your graphing calculator, as I did here, and we're using the Math 9 feature. In both cases, here's the first one, with the vertical up and down, I got an answer of 2. Going horizontally, side to side, I still get an answer of 2. It's off a little in decimal accuracy, way far out. We're not going to really worry about that at this moment. It's how the calculator processes area, but it is accurate to at least 3 decimal places, and that's our area of concern. And then when I type it in, even though I wrote it in terms of y, I just type everything in my calculator with just x's. So I notice I replace all the y's with x's just for typing it in. But when I write it, it's in terms of y because it's side to side. My next example is the region found y equals x squared plus 1, y equals x minus 2, and 2 vertical lines at x equals negative 2 and x equals 2. You're going to have to choose whether you want to do it up and down or side to side. If I do up and down, you ask yourself, is the same curve always making the top and the bottom, or does it change? If it changes, then you'd want to go side to side. So for this one, the parabola always defines the top of the region of area and connects to the line at the bottom. If I tried to go side to side, you'll see I'd be cutting into the parabola, and I'd have to make a jump. That is very difficult to do, so we don't want to have things where we cut into open space and jump to another curve. You want to clearly go from one curve to another. So I'd go from the parabola down to the line, parabola down to the line, parabola down to the line, all the way through from negative 2 to 2. So this integral's area would be the sum of the infinite rectangles starting at negative 2, ending at 2. The height of each and every rectangle is found from taking the top curve, which is the parabola, which is my x squared plus 1, and then I have to subtract the bottom. The bottom curve happens to be a binomial, so I have to be careful because I'm subtracting more than one term. I need a grouping symbol to say minus x minus 2, minus that group, close the parenthesis to represent the height, and then dx for the width. And that's my setup for the area. I'm not going to calculate that because I have many more problems to do here. My next example, I have y equals negative x, y equals the square root of 6 minus x. If I try to go up and down, if you notice here, I start at the square root function and I drop to the diagonal line, square root, diagonal line. But notice right here, there's a changeover. Curves are crossing. That's what you want to be on the lookout for. If your curves are crossing, then it changes who's defined as the bottom curve in the region of area. Now it switches from the diagonal line to a horizontal line. generating two different bottom curves, which would mean I'd need two different integrals because I'd have to split it into two area functions, which can be done. However, I want to do it as one integral, so I'm going to go side to side. If I go side to side, I always go from the same curve on the right, because it would be the square root function, it goes to the diagonal line. Square root, diagonal line, square root, diagonal line, square root, diagonal line, square root, diagonal line. So this is a case where going side to side makes it easier because I'm dealing with one integral. If I'm dealing with side to side, I have to do everything in terms of y. So that means first thing I have to do is convert everything to an x equals to get it in terms of y. So I'm going to square and then flip-flop. So now I have the function on the right in terms of y. The function on the left, y equals negative x, is easy to get in terms of y. It's negative y. So these are my two curves that I'm working with. To find the area, I would say area equals the integral from, starting value is the y value at the bottom of this. So I start at 0, make my way up to where I would stop collecting horizontal strips, which is at 3, and then it has to be right minus left. The right is the first one I did, which is 6 minus y squared, minus the left, which is down here. So I'm subtracting a negative y, so I'm just going to say plus y dy. So that's the sideways case. Next, going to need our graphing calculator again for these. What happens when we cross at some non-nice points? So I have 4 sine of x over 2, and the other curve is x squared minus 3x minus 2. Here's my sine curve, here's my quadratic. Their points of intersection are not nice, okay? So what happens in these types of scenarios, I'm using my graphing calculator. I'm going to let y1, and you can type that in, let y1 equal the 4 sine of x over 2. Let y2 equal x squared minus 3x minus 2. Then set your window so that you can see, before you hit enter or graph, go from -5 to 5, -5 to 5, and make sure you have a good viewing window for that graph. So there's my two equations, and then I'm plotting them on a -5 to 5 domain and range. What I want to do first is find those intersection points. So I hit second trace to get the calculate menu. 5 is the intersection feature. It's asking me for my first curve. So I have to use the left or right arrow key to move the cursor to that first intersection point. Hit enter. It's already there, so I'm going to hit second curve, enter, guess, enter. It's reading off my first intersection point as being -0.373, I want to store that because I need to know where I'm starting and ending, and they're both not nice values. So at this point, I'm going to hit second, quit. I'm in my home screen. If I hit X and then enter, there's that value of the intersection point, and I don't want to lose accuracy. So I'm going to hit STO for store, and I'm going to store it in A, like I'm going to assign it a value for a variable. So I'm going to hit alpha math to get the A, and then I'm going to hit enter. So now A is this value right here. I go back to the graph, and I want to get that other intersection point. Second, trace to get that calculate menu. Go to 5 for the intersection. Right arrow key is going to scoot me along the curve. and I keep scooting along until I get over to that second intersection point. And then I hit enter, enter for the second curve, enter for the guess, and it's telling me my next intersection point is at 4.263. If I hit second quit, and then I hit X, enter, there's my second intersection point. I want to store that, so I'm going to hit STO for store, alpha, and now I'm going to do B, so I'm going to hit apps to get just the B, enter. So my A value and B value have been stored in. So when I want to calculate the area, here's what I'm going to do. I want to say the area between these two curves, so this is what I'm looking at right here, goes from A, because I have defined what A is, to B, because I have defined what B is, and I highly recommend defining what Y1 and Y2 is, and then defining the A and the B, because then when you go to set up your area integral, all you have to do is say the top curve is stored in Y1, and I've defined it, minus Y2 dx. And then I'm in the home screen of my calculator, math 9. I hit alpha math to get the A. I hit alpha apps to get the B. I go over here to get the Y1 and the Y2. I hit alpha trace to get that F4 menu. Y1, I'm just going to hit enter, minus alpha trace to get that Y1 menu. I want the second one down, enter. Go over it and say dx. Once I hit enter, I've got everything I need, and it's 22.597 with 3 place decimal accuracy. 22.597, 3 place decimal accuracy. Okay, and then look at the integrals not so cluttered with everything defined above. My last example is what happens when curves cross multiple times. You're generating, in this case, we're generating 2 regions of area. So right here, we've created 2. All right, depending on how many times you cross, you can have more than that. So for this one, I have defined my y1 to be the cubic and my y2 to be the linear function. So I set the calculator up so that those are in the calculator. My intersection points, I designed it so that I wouldn't have to go through that process again. I made them kind of nice. So we're going from -4 to -1. And then be very careful, because the top curve is the cubic on this particular region. The cubic is in y1. So I'm going to say y1 minus the bottom curve is the linear function. So that's y2 dx, plus the next region of area goes from -1 up through 3. And you could always put this into your graphing calculator and just verify that those are indeed the intersection points. And then for this one, notice the flip-flop. The linear function is on top, so now I'm going to say y2 minus the cubic is on the bottom, so minus y1 dx. I'm going to take my graphing calculator. There's my y1, there's my y2. Okay, I'm going to hit second quit and be in my home screen. Clear that old one out. So I'm going to say math 9. I'm going -4 to -1 of alpha trace, and then I want y1 first minus alpha trace y2 dx plus math 9 from -1 up through 3, and then I want alpha trace y2 minus alpha trace y1 dx. X. Hit enter, and I'm getting a region of area total of 78.083. So 78.083. And that's it for today's lesson on area between curves. Thanks for watching.